constant of proportionality. Now, you could think of this one as something that is similar to the common difference that we discuss in arithmetic progression, or you could also think of this the ratio, the common ratio in um, in geometric progression. So la- to better understand this one, let us have these three different case. So case one. Okay, our constant of proportionality here is actually symbolized by k. Okay, so that's why we have here in the first case we have x variable equals to the constant proportionality k times y. So for case 1, it states that if x is directly proportional proportional to y, so if this is the case, if x is directly proportional to y, I want to highlight this term or these terms, directly proportional. It means that if x increases, we would expect that y should increase. So if x decreases, we would also notice that y as well decreases. That's the meaning of this term directly proportional. So x is directly proportional to y. So whatever change happened to y, x will be affected by that change. If y increases, then x increases. If y decreases, then x decreases. That's what we mean by directly proportional. So generally, this statement is written in this standard form. Okay, written in the standard form, x is directly proportional to y. So the constant of proportionality here is k. You could see that x divided by y, it gives you the constant of proportionality k. Okay, this is similar to what we understand about the concept of common ratio r. Okay, but the thing here is that this is how we write or create an equation if the statement is directly proportional, if two variables are directly proportional from one another. And this is how we get the constant proportionality of the said equation. Now if we place this one in a rectangular system on x and y plane, okay, let's say um, this is our x and this is our y. Let me create another formula here, and I will just simply reverse the variable. So I would say y if y is directly proportional to x, then I would write that y is the constant of proportionality times x. Okay, so the value of y changes depends on the value of x. So if I will try to graph this one, it would something look like this. It should give us a straight line. Okay, so that's what we mean by directly proportional. That's the graph. Now for case 2, okay, for case 2, let's say if x is inverse proportional, okay, so for case 2, the statement here is that if x is inverse proportional to y, it means the term here, inverse proportional, this one, inverse proportional, this is opposite to the case 1. So it means if x increases, you would expect that y should decrease. If x decreases, then the value of y should increase. That's the meaning of inverse proportional or inversely proportional. So this is kind of opposite to case number 1. Now, how do we write this one or convert this one to an equation? So we state here that x is inversely proportional to y. So I have here the constant of proportionality over y. Okay? So, or if we want to get the constant of proportionality, we would say x times y give us the constant of proportionality. Okay, so what if we reverse the variable? We would say y is inverse proportional to x. So this would mean that y is equals to the inverse proportional constant and over x. Okay, like that. Now, if we try to graph this one, if we try to make sense of this uh, equation, it would look like this. So this is our x, this is our y. So our graph here for inverse proportional, it would look like this. So as x increase, y increases, x decreases. As x increases, y decreases. So that's what we mean by inverse proportional. Let's proceed to case number 3. So it states here that if x varies as y and inversely proportional to z, so um, x changes as y changes. So that's the meaning here. So if we change x, if we change y, there is a corresponding change to x. Another thing here, it states that x is inversely proportional to z. Okay, so it means that x is also inversely proportional to z. My bad. Inversely proportional to z. So that's our k here. So our final equation should look like y k or k y over z. So that's the meaning of that statement. X varies as y, as well as x is inversely proportional to z. Allow me to read the problem. So the volume of the cone, again, volume of the cone. So the volume of the cone, again, the volume of cone varies jointly. So meaning the volume of the cone depends jointly to its height and square of its radius. So let us first focus there and convert that into an equation. So the volume of the cone, let's say solution. So volume of the cone, let's put that as V, varies. So it depends, or the volume may varies. That is depends jointly. So meaning we would expect more than one because this is two jointly to its. So we have to put here K. Okay, so no statement for inverse proportionality. So we would expect that this is directly proportional to the height. Let's put it H and square of the radius. So we have here R squared. Okay, so that's the statement there. So we have this equation based solely from that statement. Now next, let's proceed. It states here that if the volume of the cone is, now we have a condition here. It states here that if the volume of the cone is 32 pi, that's cubic inches. Okay, well, for now, let us forget about the units. Okay, 32, that's the volume, then its radius should be 4 inches. So the radius should be 4 and the height h must be 6. Now we were asked here to find the volume of a cone when the radius, so we have to look for the volume of the cone. Okay, this is for the second statement here. So find the volume of the cone when the radius, if the radius is 3 and the height is 5. Okay, so that's it. Now, based solely from this data, this is our first condition, okay? And this is our second condition, which is what is asked in the problem. You have to solve for the volume of the cone. Now, you would notice that the R here from the first condition is greater compared to the second, as well as the height is greater compared to the second condition. So we would expect that our volume for this one must be less than the volume of the first condition, should be less than that. Okay, so we have here our equation earlier based from the statement of the problem. So initially here, our goal here is to find the constant of proportionality, or the value of k. Okay, let's solve for the value of k so that we could solve for the value of the volume of the second statement. So for k, let's derive that one. That should be v equals k h r squared. So to omit hr, we have to multiply both sides by hr squared so that we could cancel out that one. And then what's left is v v over h r squared equals to k. So we will reverse this one. So this become k. The constant of proportionality is equals to the volume over hr squared. Okay, let's solve for the value of our k. So simply, based from statement number 1, the volume is 32 pi, the height is 6, the radius is 4, and we need to square that one, and we get here 32 pi. Here we have 6 times 16. Okay, could factor out this one. We have 2 times 16 pi. We have 6 here and 16 here. We could omit this one, we could omit this one. All this can be factored. So this, we have k is equal to 1/3 pi. Okay, so this is the value of our k, the proportionality constant. So next thing here is we will proceed to condition number 2 and solve for the volume. So for the volume, based from the equation earlier, can be found using this equation, k hr squared. So just plug in the data here. We have 1/3 pi. The height is 5 and the radius is 3. Not forget to square that one. Okay, so I think we could simplify this. So we have here 1/3 pi times 5 times 3 times 3, because that's squared. So we could omit the 3 here and 1/3 on the numerator. So we get this value. The volume of the cone is actually 15 pi. And this is the answer. Let us have another example. So the maximum height that a rectangular beam can support varies jointly as its width and the square of its height, and inversely as its length. So that's quite a lot of variables. So first let us dissect this one. So the maximum weight, okay, so the weight that a rectangular beam, so I want to write this one here. So, solution. It states here that the maximum weight that this beam can support varies. Okay, it varies to varies jointly. So I would expect more than one variable. Varies to jointly as its and square of what? Square of its height. So let's put it here. So varies jointly at its width. How do I write the width? Okay, width. Oops, am I right? Allow me to use another color. So width and the square of its height. So h squared, and inversely as its length. So inversely, do not forget the constant proportionality here, and inversely as its length L. So this will be our equation in solving for the maximum width that this beam can support. So that's our equation. So let's proceed. Let's focus to the next statement here. Now, if the beam is 1 feet, so that should be its wide. Okay, so we have here condition number one. It states here that if the width is 1/3, let's first forget about the units, and the height is 11 feet long, well, the weight that it can support is 20 tons. Now, for the second condition, you have to find how much so similar beam can support. So we have to find the maximum weight that another beam can support if the width is 1/4, while the height is 1/4, and the length is 17. Hmm, my bad. This is my bad. This is 1/2. My bad for that. Let me correct this one, by the way. So our height here is just 1/2, while our length here is actually 11. 11. So height is 1/2, length is 11. First thing that we should know is the value of k. So let's start there. Step number one. Step one, find k. So based from this equation, k is actually equals to uh, the weight times the length divided by the width times the height squared. Okay, so based from condition number one, we could find or substitute that data here, so we could get the value of the k. We know that the weight is 20 tons. Sorry, forget about the units. 20 tons, while the length is 11. For the denominator, the width is 1/3. The height is 1/2. Then we have to square that one. So we get, for the numerator, 20 times 11, we have 220. 1/3 times 1/4. So we have 220 over 1 over 12. So we have 220 over 1 multiplied by the reciprocal of our denominator, which is 12 over 1. So we get 220 times 12, and we end up with 2640. Okay, so that's the value of our k. Now let's proceed to step number two and solve for the value, the maximum weight that this beam can withstand. So step number two, find W. So going back from our first equation, the width is k, the weight equals to k times the width times the square root of the height over the length. K is 2640 multiplied, which is 1/4, times the height, which is 1/4, square that one, divided by the L, which is 17. So we have here 2640, 1/4 times 116. Okay, then divide this one by 17. Just simply use our calculator here. And we get 2.43 tons. So this is the maximum weight that this beam can support.